It's a delight to welcome you to the Blavatnik School. And on behalf of the Inamori Foundation, who I'm thrilled to say are here with us today, and my colleagues at the Blavatnik School of Government, to welcome you to the first of this year's Kyoto Laureates Lectures. And let me just say, it's a real pleasure to see so many scientists and mathematicians in the room. And please know that you're always welcome here at the Blavatnik School of Government. Governments across the world need more of you, not less of you, so do engage with us. This year, the 2023 Kyoto Prize laureate in basic sciences is Elliott Lieb, as you all know, one of the foremost mathematical physicists of his generation. He did his Bachelor of Science in Physics at MIT, and then his PhD in this country at Birmingham University. He's the winner of so many awards, among which the Heinemann Prize for Mathematical Physics, the Birkhoff Prize in Applied Maths, the Max Planck Medal of the German Physical Society, and in 2022, he received the American Physical Society Medal for Exceptional Achievement in Research. We're thrilled that he's one of the 2023 Kyoto Prize laureates. And let me thank in advance today my Oxford colleague, Shivaji Sondhi, the Wickham Professor of Physics. Thank you for joining us. Shivaji shared time at the University of Birmingham with the at Princeton, a small university somewhere in America. Shared time with Elliott Lieb, and he will moderate the questions and answers today. So without further ado, would you welcome to the stage the 2023 Kyoto Prize laureate in Basic Sciences, Professor Elliott Lieb.
Good morning. Ohayou gozaimasu. I am very grateful to the Inamori Foundation for awarding me the 2023 Kyoto Prize in the Basic Sciences. And I thank the Blavatnik School of Government at the University of Oxford for their hospitality. I am happy to present the following reflections on my work and life. Although I was born in Boston, USA in 1932, it was in New York City that I grew up and formed my view of the world. My family was middle class, but New York City offered a very high quality, free public education. I discovered that I like to build things and to participate in amateur or ham radio construction and communicate with people all over the world. My Morse code eventually reached the level that I could do this, which was hard work, and I passed the examination with a license W2ZHS to transmit and connect with other people. These early efforts, in which my older cousin was influential, was leading me, I thought, to a career in electrical engineering. When I was 17 years old, my family moved back to Boston, and I was privileged, with encouragement from the eminent physicist Victor Weisskopf, to go to the Massachusetts Institute of Technology. Shortly after entering MIT in 1949, my outlook changed during my very first physics course. Matthew Sands, who co-authored the influential Feynman lectures, showed me the intellectual beauty of Newton's equations and Newton's physics. At first, I had difficulty grasping the contents because my high school classes had not really prepared me for this, for the deep understanding that a theorem such as Newton's equation, F equals ma, means exactly what it says and nothing more nor less. You might think that's easy, but it's not easy. In order to find A, one must first find the magnitudes of the force and the mass in different applications. It required half the duration of the course, plus Matthew Sands's patient help, but I finally understood the significance of the equation, and my career in science was off to a good start. Newton's contemporaries must have had similar difficulties. Thus, I gave up engineering and changed to a pure physics course for the rest of my studies. As an undergraduate at MIT, I was lucky to get a part-time job in the group working on one of the very first linear particle accelerators at MIT. This 17 million electron volt machine, which was big then, but infinitesimal now, was built by two of the nicest and most encouraging people I ever met, Isaac Halpern and Peter Demos. Unlike the science of chemistry, physics was a subject not very well known to the general public in 1949. And my father thought that my sudden career decision into physics would lead me into poverty. It turned out otherwise. And I was lucky to ride the post-war wave of government funding of science with a decent standard of living. Mathematics played a role in my studies, but not a big one. I was most fortunate to learn advanced linear algebra at MIT from Isidor Singer of Atiyah-Singer index theorem fame, and we became good friends. After graduating from MIT, I wanted to get out of my cocoon and see something of the world. Up to that point in time, I had traveled rather little, apart from large American cities. Professor Weisskopf, with whom I did my senior thesis on relativity theory, thought that the Department of Mathematical Physics at Birmingham University in England, with Professor Sir Rudolph Piles and lecturers Sir Sam Edwards and Jerry Brown, was one of the best places in Europe to do theoretical physics at that time. And they spoke English, which was important for me, since I had no experience to any other language. John Bell, who went on to invent extremely important inequalities in quantum information theory, was a fellow student, as were James Langer and Stanley Mandelstam. During those years, I did manage to fulfill my quest to visit most of Europe. After 3 years at Birmingham, and with an uninspired PhD thesis of little value, I graduated in 1956 with a PhD degree. My next stop was Kyoto. Why Kyoto? My uncle, who owned an art bookshop in Boston that specialized in Japanese art, inspired in me a deep interest in Japanese woodblock prints, ukiyo-e. In Birmingham, I was lucky to share an office with a Japanese nuclear physicist, Shiro Yoshida. I was asked to help him improve his English, and he reciprocated by teaching me elementary Japanese without any written characters, so I spoke as an illiterate. Nevertheless, the US Fulbright Commission gave me a one-year fellowship to Kyoto University's Yukawa Institute for Theoretical Physics. That year was formative for me culturally and scientifically. Up to that point, I wondered if I would ever be able to contribute anything of value to science. In Kyoto, I did just that, or so I felt. That is to say, I managed to contribute something of minor value, but of something. After Kyoto, it took another 4 years to do so again. In the Yukawa Institute, I met a brilliant young Japanese physicist, Yamazaki Kazuo, with whom I formed a close collaborative association. Together, we worked on a challenging problem in physics, the Polaron model of an electron trapped in a crystal. It was a popular topic at the time, and we decided that we were going to go beyond intuitively motivated calculations and try to compute the Polaron's lowest energy in a mathematically rigorous way. We were able to prove that the Polaron energy was actually finite. In other words, that a lowest energy exists. Other physicists like Feynman took this for granted, despite the fact that similar-looking models failed to have a lowest energy. In this way, we opened a new chapter in our lives, as well as in the theory of the Polaron. Thanks to my stay in Kyoto, I was now convinced that I could actually do research. 2 years later, I met Richard Feynman himself at Cornell University, and he asked me about my interests. When I told him proudly what I had done in Kyoto, his rather aggressive reply was, "Real physicists don't do that sort of thing." In his opinion, I was wasting my time. As a young beginner, that negative encounter set my sail ever more firmly toward mathematical physics and its importance to physics. From Kyoto, I went for a year to the University of Illinois in Champaign-Urbana, followed by 2 years at Cornell University in Ithaca, New York, under the famous Nobel Prize winner Hans Bethe, who was the one who explained the nuclear reactions that power the sun. Alas, those 3 years produced nothing. It made me uncertain again about my future as a mathematical physicist. But it did lead me to a problem that occupied me for the rest of my life, namely the quantum mechanics of a certain gas of atoms called the Bose gas, especially its coldest or lowest energy state. Thus, I spent 2 years at one of the best institutions of its kind with one of the world's greatest physicists, and came away in 1960 with nothing to show for it except for a boson problem to continue thinking about. It laid in my mind for 36 years, until Jakob Ingwersen and I solved this boson problem in 1996, and thereby started the current interest in Bose gases among mathematical physicists. From Cornell, I moved to the IBM Computer Research Center in Yorktown Heights, New York, which had just opened that year, 1960. It was my first permanent position, although I stayed with IBM only for 3 years. I was lucky to find 2 colleagues my age there, Ted Schultz and Daniel Mattis. We 3 physicists felt that we wanted to prove some accepted theories by thinking mathematically. This interest of ours was outside the realm of research in any other research laboratory at the time. And we were thankful that IBM gave us this freedom. In general, 1960 to 1970 was a wonderful decade for physics research around the world. Several theorems of importance to physics came from this period. One was the Lieb-Mattis theorem that magnetism never occurs in one dimension, meaning in a simple chain of atoms. Most theorists at the time, including Heisenberg and my old Birmingham PhD advisor Piles and my Cornell mentor Bethe, thought that the very opposite. Namely, that ferromagnetism always occurs in one dimension. And you can find that in Piles' book. And it took some effort to convince colleagues that we were correct. Piles in his book called it a surprise in theoretical physics. Mattis and I also developed theorems about Heisenberg spin models, which are still useful today. In the second of those 3 years at IBM, I was on leave in Sierra Leone in West Africa to teach applied mathematics at the university in Freetown in Fura Bay. There were many adventures of a social, political kind there, as well as a bout of malaria. But I also had time to think about science. It was there that I invented the model of Bose particles, or bosons, in one dimension, which I worked out later with Werner Liniger when I returned to IBM. This model is fundamental for understanding the quantum mechanical many-body problem. And it has even been confirmed experimentally, even though our model is only a model for a chain of atoms. After 2 years at Yeshiva University in New York in 1966, I moved to Boston again to take a professorship at Northeastern University. There, Professor F.Y. Wu and I wrote the most cited paper ever in Physical Review Letters about the exact solution of the one-dimensional Hubbard model. It continues to be the most cited paper ever in Physical Review Letters. I now turn my interest to ice. What does ice have to do with mathematics? One other important exact solution was made at Northeastern University, this time to the combinatorial problem of two-dimensional ice. The story goes back to the experimental result that the entropy of ordinary water ice at absolute zero temperature is not zero. So something is still wiggling even at absolute zero temperature. And it turns out that the significant arrangement of oxygen and hydrogen atoms is such that the oxygen is solid in a lattice, as you expect in a solid, but the hydrogen atoms wiggle around in there. And the question is, how much wiggle can it have? And that wiggle is the entropy. There is still some sort of life left at absolute zero. The explanation came from the two-time Nobel Prize winner, the chemist Linus Pauling, who said that while the oxygen atoms are nicely arranged, as I said, the hydrogen atoms are not. One hydrogen atom lies between every pair of oxygen atoms. But the hydrogen atom is closer to one or the other of the two oxygens that it lies between. And there is the ice rule condition of Pauling, which says that each oxygen has two hydrogens close to it and two atoms of hydrogen far from it. The entropy is the logarithm of the number of ways to make such an arrangement of hydrogen atoms. Count the number of ways. The slide shows the two-dimensional version of the problem. The vertices represent an oxygen atom. The arrows show the way in which the hydrogen between the two oxygen atoms is displaced. The ice rule requires that two arrows point into each oxygen and two point outward. Andrew Leonard observed that this counting problem is identical to the following coloring problem. How many ways can we cover a tiling with squares using 3 colors only, not 2 as in a checkerboard, but 3, so that neighboring squares always have different colors? You have 3 colors, each square has 1, but they're never together. The answer that I found when there are many squares, say n, is the following. It's 4/3 to the 3/2 n, which is 1.5396 to the nth power. And 4/3 to the 3/2, of course, as everybody knows, is 1.5396. It's been called Lieb's constant. This result gave birth to a whole subfield in combinatorics called the 6-vertex problem. A few months after its publication, there was an offer of a professorship at MIT, which I accepted. During the next few years, a high point was my work with Joel Leibowitz on the existence of the thermodynamic limit for Coulomb forces. This theorem, together with Freeman Dyson and Andrew Leonard's proof of the energy lower bound for electrically charged particles, proved the stability of matter. The stability of matter is a fundamental problem which can be briefly stated as follows. Consider an atom, which can be pictured as a nucleus surrounded by electrons. This picture is crude, but not wrong, and raises the fundamental question that troubled people around 1900. Why do the electrons not fall into the nucleus? Quantum mechanics explains this nicely. Why then do atoms, which appear to be as fragile as a spider's web, not collapse into each other? Quantum mechanics comes to the rescue again, but the explanation this time is very complicated. Atoms can attract each other, but only very lightly, and they retain their identities. Unraveling this story took several decades of mathematical research, and I contributed to some of this. The solution to this problem required contributions from various people, many people. This line of research is one of the most important examples of the contribution of mathematical physics to our understanding of physical reality. Other examples of my work at this time period are the Braskamp-Lieb inequalities with the young physicist Hermann Braskamp. These calculus inequalities relate integrals of products of functions to products of integrals of those same functions. I was surprised to find later that theoretical computer scientists often use these inequalities in their work. In 1975, I accepted an offer from Princeton University jointly in its mathematics and physics departments. In the same year, Walter Thierry of the University of Vienna, one of the world's most famous mathematical physicists, and I struck up a friendship and set to work to find an alternative to the Dyson-Leonard proof of the stability of matter. That proof was rather complicated, and we felt there should be a simpler one, and we managed to succeed in that effort. Let me conclude by mentioning 3 other works done at Princeton. One is the bound for atomic exchange correlation energy in quantum mechanics, which is the glue that binds atoms and molecules together. This is another result originating at Kyoto, because I had the idea for finding limits to this particular quantity during my second year, and which was 1979. The bound I found in Kyoto was a weak one, however. A year later, with Stephen Oxford at Princeton University, we refined it enough to make it a bound closer to reality and thereby make it truly useful for computations. A second equally influential paper was A Touch of Japan, or has a touch of Japan. This is the AKLT model of electron spins named after Ian Affleck, Tom Kennedy, myself, and Tazaki Haruaki, who was a postdoctoral researcher with me in 1987. It proved an older conjecture in physics, which is that it is possible to have a gap between the ground state energy and all the other energies in a truly quantum system of particles. The last work that I will mention that I regard as one of my deepest is the 1990 paper with Jakob Ingwersen on the meaning of thermodynamic entropy. A real-world example is the question, how much work can you get out of burning a block of coal? The true meaning of this question and its answer is not about jiggling atoms and other models that date back to Boltzmann. Rather, it can be defined without any mention of temperature or cycles or models or chaos. In our view, with Jakob Ingwersen, it's simply a quantity whose increase defines the necessary and sufficient condition for any proposed process to take place. That is the meaning of entropy. Its fundamental existence is guaranteed if certain simple axioms are satisfied. Many people like our point of view, but some people think it is irrelevant. Which reminds me of my earlier experience of such an attitude from Feynman many years earlier. Even in the hard sciences, taste plays an important role, and people can disagree about the significance of a particular line of research. In this talk, I have touched on several areas of mathematics and of physics, and the combination of the two. I have been fortunate to interact with many exceptional colleagues in several countries, and to have received enough support and encouragement along the way to persist despite initial doubt. I thank the Inamori Foundation again for awarding me a Kyoto Prize and for the opportunity to present these reflections on my life and work. Thank you.
Working now? So first, on behalf of all of us, I'd like to thank you for an absolutely brilliant talk. And I think maybe I can say just a couple of things about Elliott in addition to all the other stuff that you either know or have read in coming today. You know, there's sort of physicists who are well known to a larger world because they work on questions that are easily understood, you know, by other people who are not physicists. The people who are very well known because they're very good at explaining their answers, whether the answers are correct or not. But then there are people like Elliott, who properly described as sort of physicist, the sort of people to whom professional physicists turn when they're confused about things. So his work really is the kind of, if in private conversation when he's not around, some of us would say, well, okay, this is what I think. It's not a theorem by Lieb, but nevertheless, this is the best I can do. So that's his status in the field. I came as a young assistant professor to Princeton. We were colleagues for 25 years. He was, of course, already a legendary figure when I reached. And having been in places where there are legendary figures, I can say that in some cases, you were better off knowing them as legends. But in Elliott's case, my admiration for him just grew linearly with time, and I was one of the tragedies of leaving Princeton and coming to Oxford was to not have him down the floor anymore, to talk to. With all of that said, maybe I'll start off with a few questions for him, and meanwhile, I'm sure you'll all want to jump in. Actually, I mentioned one quick thing. You talked about the work on the second law. So there is at least one person in this town, David Deutsch, who, in fact, does take your reformulation of the second law seriously and would like to reformulate all of physics. He calls it, he and his collaborators call it constructor theory, in which somehow the laws of physics would be reconceptualized as limits on processes more broadly, not just that. You mentioned a bit about Feynman. Would you maybe mind telling us a little bit about other interesting physicists that you interacted with? I mean, I think Dyson was someone you worked with, Onsager, and maybe a bit more on Feynman, which...
Well, let's see. You mentioned Onsager. Well, I did meet him once. Mm-hmm. And he is not very easy to speak with because he's slow. He's not slow, but he's shy a bit. And I met, of course, Thiering, as you said, and Walter Dyson, Freeman Dyson, sorry, and who else? Many people. And I've had the pleasure of interacting a lot with Barry Simon, with Joel Leibowitz, I think I mentioned that, and with Michael Loss, which you may know, who's a mathematician, and too many people to remember, or not remember, but recount.
Are there people that, maybe one or two that were particularly memorable in terms of either personalities, intellectual styles, or that you?
Oh, well, the person I interacted with most is Michael Loss, I think, mm-hmm. who's a mathematician, but also he started out as a physicist from Zurich, and we decided to analyze many concepts that were current in physics and see if we could find some mathematical foundation and maybe even find something new. I've already mentioned Joel Leibowitz, with whom I first got interested in the stability of matter problem, and we proved that. Two things. Let me explain stability of matter. Matter is stable. You can knock it and it doesn't move. Now, why is this so? Because it's made up of atoms, and the atoms are like thin, like a spider's web. There's nothing in an atom. It's a few electrons running around. But somehow it's stable, an atom. And the question is, why are the atoms together so stable that I can pound on them? That's a difficult question. And it occupied many, I won't say many, that's not correct, some serious people for many, many years. It's not a simple question to answer. Why don't they just become like liquid or jelly or whatever? Why it's solid? And well, the answer to that question, as I said, is not so easy. But it bothered people. I think it bothered people at least since atoms were believed, which would put us at the end of the 19th century, when people really believed in atoms and came up with the obvious questions. If an atom is a little ball, why do the little balls stick together? I mean, in such a nice way. But they're very stable, but they stick together. This is not an easy question to answer. And that took many, many years to straighten out with contributions from many people, one of which is our chairman here and our interlocutor.
Moderator is my official title.
So that's, we'll go on to the next question.
So maybe segueing from that, so you trained as a physicist, but increasingly became a mathematician, or at least a mathematical physicist. Since you're a member of both tribes, do you have any comments on your sort of...
Yes.
Yeah.
By the way, that was not planted. It's his own question. And, well, I think mathematics has a lot to do with physics, and physics has a lot to do with mathematics. Now, it's a sad fact that very few mathematicians believe that, and very few physicists believe that. I will not discuss present company. But it's a fact. And physics would certainly not have progressed as far as it had by rolling balls down inclined planes. I mean, you can only go so far with that. But even Galileo understood you needed mathematics to understand what was going on. And always the best physicists understood this fact. The question was how far to go. You can go overboard, of course. And that's a difficult question. And I, my own self, feel that one can go pretty far. And you can get new physics out of mathematics. At least new questions, I should put it that way. And therefore, the understanding of mathematics, especially with the introduction of quantum mechanics, which really is a mathematical theory, changed the outlook of physics. It shows that mathematics must be really integrated properly into physics. And that is not always so easy, especially in condensed matter physics, at least historically. In fact, there were people, like, as I mentioned, like Feynman, who thought that mathematics had no business in physics, although he himself did some mathematics. People are sometimes self-contradictory. Feynman was certainly one. And so I would encourage young physicists here, if there are, I suppose there are some, to learn some good mathematics. Serious functional analysis if you want to do quantum mechanics. And I would encourage some mathematicians to realize that physics is one of the fundamental sources for mathematics, especially functional analysis. And so bone up on both subjects from both fields. The ball's in your court.
We don't have copies, but there is a textbook you have, but I think with Michael Loss on...
Yes, yeah. Called Analysis. Yes, right. Michael Loss and I, another mathematical physicist, now in Georgia, Atlanta, Georgia. We decided to write a proper mathematics analysis book. In fact, we call it Analysis simply. Write a proper mathematics textbook on functional analysis, but with having in the back of our heads that we're really trying to answer some physics questions. So it shows through. In fact, the first referee, or reviewer rather, of this book said, well, this is a great book at analysis, but we could see that the authors trying to think of something that may be relevant for physics. So mathematics and physics go very well together, and that has been proved now. And there have been previous examples, other examples in the past, and I hope it will continue to grow, this interrelationship between physics and mathematics.
I went to ask Elliott for an autographed copy of his textbook when it came out. He gave it to me only on condition that I would actually read it. Otherwise, he was unwilling to give up a copy. At this point, I think members of the audience should feel free to weigh in, and if not, I can keep going, but I think I'll wait to see Paul.
Just to follow up this mathematics versus physics thing. So you mentioned, oh, there we go, thank you. You mentioned this Feynman, giving you this negative feedback and that hardened your resolve. So yes. Sort of two-part thing. Was there a conscious decision that, oh, I'm going to do mathematics, or did it just sort of that happened to you, and then you realized only later that was an influence? And the second thing, was there any positive sort of feedback you got around then that inspired you to go in this direction?
Well, the first...
Did you just slide into mathematics was the first part, and the second?
Yes, I picked up mathematics on a need-to-know basis. And so eventually it had to get formalized, because you can only go so far with being an amateur. You have to become a professional eventually if you're really going to utilize it. But it starts out on a need-to-know basis. And so if you want to be a physicist, you should learn some basic functional analysis, especially if you want to do quantum mechanics. But sooner or later, you'll have to do it, learn it. And what was the second?
Was there an anti-Feynman who actually encouraged you to go in this direction?
Was it anti-Feynman?
Was there an anti-Feynman, someone who, instead of discouraging you, encouraged you to go in this direction?
No, I didn't need any encouragement. Well, it was important that, several people had influence on my life. I mean, Barry Simon at Princeton encouraged me. Walter Thierry in Vienna. These are people who pioneered in this area. And I don't know, Dyson, for example. So yes, there were a few people from whom I learned, of course, and by their example, encouraged me to continue in this direction.
David.
Can I ask you another question?
David, 1 second. I think that she would like you to.
Can I ask you another question related to what I would say the difference between theoretical physics and mathematical physics? Sometimes, quite often, at least, I find myself in the situation of looking at a problem. I then have to find a way to, first of all, be inspired. Secondly, make a model. Thirdly, solve that model. But then, quite often, when you get to that stage of solving the problem, you don't have the ability to do that, and probably it doesn't exist in the ordinary existing mathematics either. I think you probably recognize what I'm talking about. So sometimes what we have to do is either change the problem slightly to get to a form which we can have a better chance of solving, even though it's less related to the physical system, or we have to make ansatzes, or there may be limits, and we perhaps have maybe a number of limits, and the only way to make any progress is to change the limits the other way around, knowing that that could be wrong, but then you can sometimes continue and find some other results which are of interest in being different from what you expected. Mathematician, of course, has to look at the problem then and help to say whether it was right, the assumptions were right or wrong, or maybe only just whether the result was right or wrong, even though the methods were wrong. And could you say a little about the relationship between theoretical physics and mathematical physics?
Okay, I will. For the audience to know, we had the same thesis advisor, PhD thesis advisor, David and I, at Birmingham. I was Edward's first student, you were his last student, I think. So what can I say? Are you about to say something? No. How can you decide when to use the mathematics, and where it comes in, and is that the...
I think a little bit is in work, there was the replica method, right? So the tricks that physicists use, which you can't really, at the moment you use them, you don't necessarily justify them in a rigorous way, but they're often exact or seemingly controlled. There is a parameter. So there is a set of methods in theoretical physics which maybe are awaiting, and so I think that's the spirit of the question is...
I'm asking a more general question.
Right.
Often, and our role as physicists is to understand the world, or maybe for the use of knowledge. I haven't got a whole slide.
Well, okay, while we're waiting for the microphone. So the question, I think, was when does the mathematics come in? Or where?
My question is, where do the two métiers of being a theoretical physicist or being a mathematical physicist, how do you see them relating? What is the purpose, in your view as a mathematical physicist, of the theoretical physicist who will do mathematics, which isn't always perfect? They can't guarantee everything's right, but they have to do something to make a possible solution and then to come back afterwards and check whether it's right or wrong, with the final thing being given to you. For example, like Abel getting part of getting his Abel Prize 2 weeks ago.
Well, I think mathematical physics is not just crossing T's and dotting I's. Yes, and I know you're not saying that. I'm just for the general audience. And mathematics plays a fundamental role in understanding the physical world. There's no really basic something in the brain difference between mathematical thinking about the world and physical thinking about the world, although people like to make a big story about the difference, but it's really not a big difference. And I think every physicist should know enough mathematics to create things mathematically at the beginning, if possible, because mathematics is the precise formulation of what it is we need to know. It's not just a calculational device. That's not that. It's a way of thinking. And so students of physics should learn real mathematics, take real mathematics courses, and know how to think like a mathematician. Likewise, mathematicians, at least those in analysis, should learn some real physics, how to approach a problem from the point of view of a physicist. Physics is not just given an equation, try to solve it. It's not like that at all. So you have to make this bridge between different ways of thinking. But you need both. You need both on different occasions. Yes, sir.
Professor,
I'm sorry.
Wait, you have to wait till the... Yeah, could you please give it to Professor Sarkar there?
If I might be provocative, there have been examples of attempts to apply mathematics to physics problems where it has turned out to be not relevant. So one is reminded, for example, of Tate, who invented knot theory and attempted to apply to understand why atoms are different from each other. He thought there were different kinds of knots, and that turned out to be not right. Of course, knot theory found application later in superstring theory. We have yet to know whether that might have some relevance to the real world. But what I'm trying to say is that whereas there have been many examples, as you highlighted, of mathematics elucidating a physical problem, there are lots of bits of mathematics for which we do not yet know any obvious physical application, and possibly vice versa. Would you have a comment on that?
Right.
What did you say to that? I mean, you were earlier espousing that physicists ought to learn mathematics in order to make progress, certainly.
Yes.
But conversely, the opposite might also be true. If one is to solve physical problems, then mathematics by itself may not suffice because it might not be relevant to the particular problem under discussion, but to something else.
Well, mathematics is a way of thinking, and I don't think you can really do physics without mathematical thoughts in your mind. It's not possible to make it. You cannot name any physicist, historically important physicist who did not know a lot of mathematics. It just doesn't exist. And you might, well, I don't know. They could. I think everybody learned mathematics enough for the occasion. And the distinction is, in my view, somewhat artificial, and there's a bridge across. Well, you're in charge. You should.
Okay, so first the person in the front, and then Professor Essler at the back next. Yeah.
Is there a piece of research or discovery that you yourself are most proud of and feel has the most importance during your career?
I'm sorry, could you repeat the question?
Is there a piece of research during your career that you feel most proud of and feel has the most importance?
Oh, well, several. In physics, it's probably this work with Volta Tearing on what is called the Lieb-Tearing inequality, which relates the spectrum of the Schrödinger equation to an integral of the potential in the Schrödinger that appears in the Schrödinger equation. And one knows intuitively that they're related, obviously. And the question is to make this relation precise, a little bit more quantitative. And we achieved that. So that's one of the things. Does that answer your question enough? Yeah, okay, good.
Professor Essler at the back, I think.
Could you comment on a couple of key problems in mathematical physics which you think will be solved in the next 5 to 10 years?
I'm not thinking that far ahead. At 5 to 10 years, well, no, I would. You know, one thing I learned is you cannot predict the future, and it's true. Because progress comes. It's funny. It comes from different directions and different sources, and suddenly something is there. You can't see it coming, like a comet. You can't see it coming into or if a meteor. It just comes in, and I can't sit here and predict the future. But one thing I know is it's the friendship or the cohabitation of mathematics and physics gets stronger all the time, and people are physicists and mathematicians, I believe, are accepting this more and more, because it used to be that people believed there was no connection whatsoever. And I believe this will get stronger. And they will continue to be separate subjects, but the interaction or interrelation will become strong, I believe. in the next 5 years, 10 years, 15 years. It'll never stop.
Okay, one. Right. One, then two, and then three. So.
Great, thank you very much. I hope you don't mind me asking, but after you mentioned you got your first permanent position with IBM, why did you leave?
Oh, I got an offer from Yeshiva University in New York by a very persuasive individual, Joe Liebowitz, if you know him. I don't know. Anyway, they said, he said, you want to get back into academia, he said. Come to New York. And Yorktown, you see, is not very far from New York. So instead of driving every day to Yorktown, I would drive every day to northern Manhattan. So that stayed with me. It's the toss of a coin.
You said that in your early career, you had several bouts of fairly mediocre results. Well, that was the impression I got. What kept you going through that? I speak as the father of a boy who's just starting in mathematical physics, and I want to know how to maintain his impetus if he has problems.
Well, I don't know. It's difficult to say because you're now asking me correctly about an age that I no longer resonate with. I mean, I've passed that stage. A young person, there are people who are like both physics and mathematics. And eventually, it's in the mind, it comes together that these are not so different subjects. And that is something that has to come from inside. I would not push anybody in any direction. I'm not saying you are, but I would not try to do anything like that. But I believe they belong together. And that's not popular with many people. But the person himself has to feel this way. Otherwise, it won't work.
So in the several decades since Feynman made that comment to you, I think there have been like a large number of so in the decades since Feynman made that comment, I think there have been a large number of maybe very surprising connections between physics and a whole host of areas of mathematics. I think even in condensed matter physics. And I was wondering if there's any particular connection that you, any particular discovery or connection of a connection between mathematics and physics that you found particularly surprising or unexpected within that time.
Did I find something that is truly surprising? That's the question.
Yeah, specifically in the realm of connections between mathematics and physics.
Course of your career. Not necessarily something that you were personally involved in, but was there a connection developed between physics and mathematics that you found surprising? More
oh, I see. By other people, not by myself. Well, the whole the answer is no specific thing in my case, but there's this symbiosis between is natural. It's the same brain working, and so history shows many good examples. And the first part of the time, the hard academics said these subjects have to be separate, but there are people who just intuitively understand that they belong together. And this has happened throughout history many times. So there's nothing more to be said about that, I think.
Just to balance, yeah. If you, this gentleman in the front.
Thank you. I noticed one item you've mentioned in your work, which is possibly chemistry related. Being a chemistry graduate, I can tell you that we learned very little about the hydrogen bonding, except to say that it occurs in ice and this is how it works, in the negative and positive attraction. What I was curious to know is, first of all, that ice retains some wiggle room, as it were, but is there any other heterogeneous solids that you've found retain this energy at the 0 degrees?
So I didn't.
Are there other materials that violate the third law, have a macroscopic entropy at low temperatures?
And what is the question?
So apart from ice, are there other systems?
Oh, yes. Carbon dioxide has a lattice ordering. And where else? There are many examples of this.
Spin ice.
Spin ice? Well, spin ice is like, yes, like ice, but yes, okay, that's true. But just in nature, there are other examples, certainly. Okay.
Do you believe that other heterogeneous systems would behave the same?
Not some will, yes, some do. Yes. I think the lady back there has a question.
Hi, thank you for a fantastic talk. It was really brilliant. I just wondered what you're researching at the moment.
Oh, trade secrets. Huh? No, you know, things just fall into your lap. They're either there or not there. At the moment, there are things I'm interested in, but I don't want to talk about this publicly because the chances are I will not solve them in my lifetime, but these things keep coming up. That's all I can say.
All right. I don't know how we are on time, but just look at. Okay, we have some time. Okay, so there was a person. Others who are interested to raise their hands now, so I can sort of. Okay, so maybe 1 and 2. All right. We'll 3. Yeah.
Can you say 2 words about your approach to the second law of thermodynamics and how it differs from the standard textbook one, say?
Yes, what is it?
So your approach to the second law within Gavson and how it differs from textbook presentations of the second law, the textbook logic for the second law?
Oh, very much, because the second law seems to come in the textbook story, certainly by looking at examples, cycles, and they don't come back and do things. And that's the usual approach, and that's the historical approach, Clausius and people like that. Our approach is that there has to be an entropy function. It just has to be, provided some elementary axioms are true, which they always are. Or maybe they're not always, but anyway, there are provided there's certain rules of the game, then there will always be an entropy function. Whereas the historical approach is, hey, look at all these examples. So they must be linked in some way, and that linkage is something called entropy. But that's not our approach. Our approach is there has to be this entropy. You just can't get away from it. It's not an accident.
In physics today, he and Gavson wrote up a semi-technical account which has pictures with a gorilla in it, and no textbook on the second law has a gorilla in it, so that one certainly is a difference, yeah. That's right. And there was someone on this side, I think, yeah.
I actually read your manuscript on the second law stuff, and you formulate a second law as an equivalence relation, like adiabatic equivalence. but I still like don't understand like how quantum systems generalize. Does your formulation actually solve that problem or not?
He now wants to talk about quantum systems and thermalization and whether your way of thinking about the second law would apply to.
Oh yes, why not? The axioms are very simple, and they are true in quantum mechanical systems as in classical systems, so there has to be an entropy function. The second law, for people, for the audience, a system like a bucket of water or whatever, anything, can exist in various states. And some states are above other states. That is, you can go in one direction from here to there, but you cannot go from there to there. So that defines a layering of accessibility. That is, and the second law quantifies this layering by an entropy function. Different states have different entropies which go up. It means you can go from one state in this layer to a state in that layer. And that simple fact, comes from just a couple of axioms. It would be true of molasses. I mean, it is, you don't need any big story about it once you understand that these entropy, the characterization of different states and different levels of states with this, it just is a natural thing. It would always be there. You don't need fancy experiments to see it. You just need a little logic. Okay, maybe you have to talk.
So, for example, we see different systems behave differently, like the bottle and water. Like water is more thermal, while like a glass bottle is not that thermal to my appearance.
I'm going to suggest that probably at least a few people in the audience who were not looking forward to a statistical mechanics class. So when we're done, you can take it up. And meanwhile, maybe on the other side, yeah.
Hi, so I'm a math student. I was just interested in, well, recreational maths and recreational physics, perhaps, because your talk reminded me of this other mathematical physicist called Tadashi Tokieda. He does a lot of recreational stuff. For example, you can prove V minus E plus F is 2, like on the surface of a sphere by considering an electric circuit. So like there are this kind of like playful like mathematics. I was wondering if you've ever like done things like this, or what do you think, like would this be useful for like teaching or introducing students?
You remember Tadashi Tokieda?
Tokieda.
Right. Yes, Tokieda. So the question is, do you find his methods useful in your own presentation of? Yeah.
Not directly, but I love the guy. I mean, his performances is bringing together different things that do not seem to belong together is absolutely amazing. And he's one of the great contributions of English academia to.
He has since moved to Stanford.
Huh? He has since moved
to Stanford.
But I first knew him when he was at Cambridge, long time ago, before he became popular.
Right. So is this a good time to? Would you like to?
Thanks again to both of you. That was a wonderful conversation. There's not that many talks about mathematical physics that have elicited so much laughter in the room, Elliott. So thank you for drawing us all into your world and making us curious about what you do and how you do it. Can you join me in thanking this year's Kyoto laureate and, of course, the Wickham professor who's guided this conversation so beautifully today. Thank you very much.